Okay, everybody, time for another video. So this one, it turns out naturally follows from the one that I just made. And the one that I just made was about independent events, dependent events, and conditional probability. Okay, so all of those topics and ideas, math, everything there will flow right into this one. Okay, but before I talk about how that all works out, I wanted you to think about some things to set this up. Okay, I want you to think about the kind of problems that we're going to solve in this video. So I want to talk about how you calculate the probability that certain events occur in sequence, okay? And when I say in sequence, I mean one event right after the other event. Okay, now let's give an example of what I mean by events that occur in sequence. So one example is like if you toss a coin at like 3 times and you get 3 tails in a row. So, if I toss a coin one time or, whatever, if I have some way to randomize a coin, I get either heads or tails each time. And I've got a 50-50 shot of getting tails, all right? But what are the odds I get 3 tails in a row? It seems like the odds of that would be far less likely than just getting 1 tail, all right? But nonetheless, tossing a coin 3 times, those are events, random events in sequence. I want to know, how do you calculate the odds of that sort of thing? First tosses tails, second tosses tails, third tosses tails. So those are that's one example of events occurring in sequence, and I'm curious, how do we do probability calculations on that, okay? So next example of events occurring in sequence, I guess we've seen one like this before, okay? You've got your standard deck of cards, and you draw a card from the deck twice, and then you replace the card each time you draw it, and you get the 7 of hearts each time, okay? Again, those are 2 events occurring in sequence, one right after the other. Draw a card at random, get 7 of hearts, then replace the card, then draw another card at random, get the 7 of hearts again. So you'd think, to get a 7 of hearts once has a certain probability, but to draw it twice is very rare, very unlikely, okay? You'd think the probability of this event occurring in sequence is less than it just happening one time, but nonetheless, those are examples of events occurring in sequence, okay? Now, my next thing that I think that naturally we're led into is to wonder, what are the odds of those? My instinct tells me that the odds of these events occurring in sequence is a lot less than them happening just once, okay? So let's talk about how you do the math for those kind of probability calculations. Okay, so, StatCat has something to say here. The probability of events occurring in sequence depends on if the events are independent or dependent. Now, remember I said that I said that this video would flow from the last one, and the last one was about independent and dependent events. And it turns out the way you do the calculations on a sequence of events depends on what kind of events they are, independent or dependent. Now here's how. There is something called the multiplication rule. And it gives us guidelines, gives us a formula for how to calculate the probability of 2 events occurring in sequence. So I want you to think of it like this. I wrote my P for probability, my parentheses, and then the event is this. Event A occurs, and then event B occurs, okay? So here's how you calculate that. The event A occurs, and then the event B occurs, okay? It is the probability that A happens on its own times the probability that B happens given that A already happened. So you see why it's called the multiplication rule, because you use multiplication to calculate the odds of events occurring in sequence, okay? Now, that's how you do it if A and B are dependent events. What are dependent events? Dependent events are events where one happening does, in fact, influence the likelihood that the other will happen. Okay, that's what dependent events are. And here's how you would calculate the odds of them occurring in sequence. Okay? All right, so that's the multiplication rule for events happening in sequence, one right after the other, if they're dependent. Now, what if they're not? What if they're independent? Now, for short, people usually write this probability A and B. Up here, giving it to you the first time, I wanted to say that, all right, what I mean by this is in fact the events happening in sequence, one right after the other. A happens and then B happens, okay? But for short, people write it this way, probability A and B. All right. So if A and B are independent events, the probability that A happens and then B happens is the probability that A happens times the probability that B happens. Okay, so what you want to do to calculate the odds of events occurring in sequence is decide, well, are they dependent or independent, and then use one of these formulas. Now, I wanted to do some thinking above this. At least when I was in school, I wanted to understand everything inside and out from every possible angle. And I know not everybody wants to do that, but some people do. And, I think if you're in school, you might as well get the most of it. Okay. Are these really different formulas? Okay. I wrote them here like they are, but really, are they different? Okay. They're not really different. And let me remind you that if A and B are independent events, that means that if one happens, it doesn't influence the likelihood that the other happens. And that means this conditional probability, the probability that B happens given that A has already happened, is just the probability that B happens. Okay? So this formula becomes this one as soon as you understand that the events are independent. Okay, so they're not really different. If you want to think of them as different, then that's fine, but they're not really different, okay? One of them comes from the other. Now, let's see an example about that, all right? So, I use lots of drawing a card from a deck of cards, and I know I've told you why I use that kind of example, because we're familiar with the deck of cards. And maybe you have one at home already, and it kind of gives you a way to hands-on understand this, okay? But, okay, 2 cards are selected from a standard 52-card deck. The first card is replaced before the second card is selected. Okay, all right, we randomly pick a card from a deck and then replace it, maybe shuffle it around a little bit so we're starting over, and then we select a second card. So let's think about these events occurring in sequence. The first draw is any 9, and the second draw is any king. Okay, now first of all, are these independent or dependent events, and why? All right, answer to that is they're independent. The reason, if you replace the card and reshuffle the deck, you're starting over when you have the second draw. Whatever happened in the first draw, the deck has already forgotten it. It has no way to remember. You put the card back, you shuffled it, you're starting over. That's why they're independent. What happens on the first draw has nothing to do with what happens on the second draw. Okay? So, let's see. What are the odds that, how do we read this again? A and B. What are the odds that the first draw is any 9 and then the second draw is any king? What are the odds of that happening? Well, these are independent events. Okay, so that would be the probability that the first draw is a 9 and then times the probability that the second draw is a king. Now, with 9s and kings or any card, there are, what did we say? There's 4 suits for each card. So like for a queen, there's 4 queens. And this is true for all the other cards. There's clubs, spades, diamonds, hearts. Okay, so if now, here's my formula, all right, here's my math. That's how I'm going to do the math. Then the odds that the first draw is any 9, well, there are 4 9s out of 52 cards total. So that's the odds of that first draw being any 9. And then the next draw out of that deck being a king, okay, well, what are the odds of drawing a king out of that deck? Well, there are 4 kings out of 52 cards total. So it's 4 out of 52 times 4 out of 52. All right, that's 16 over 2,704, or about 0.0059, which gives you like 0.5% chance of that happening. All right. Yeah, not real likely that you pick these cards at random and get a 9 then a king. 0.5%. Okay, that's like 1 time out of 200 about. All right. Okay. So yeah, well, there's the example of calculating the probability of events occurring in sequence. Okay, well, given that this time they're independent, let's alter things a little bit. So let's say I want to do an example just like that one up there, where we're drawing cards out of the standard 52 card deck. Okay, with events A, the first draw is any 9, and event B, the second draw is any king. But I'm not going to replace the first card I take out, okay? Now, that does change everything about this. But let's say like I got this deck of cards. I pick one at random. Sure enough, it's a 9. And I put that card aside. I don't put it back. Maybe I reshuffle the deck just to make sure that it's randomized again, okay? So that's what's happening this time. I'm not going to put that first draw back. So this time, the events are dependent, right? Why is that? Well, up here I said, if you replace the card, does the deck have any way to remember what happened on the first draw? How could the first draw influence the second draw if you replace the card and adequately shuffle it and randomize it? The deck has no way to remember what happened on the first draw. That's why they're independent. But if you don't replace that card, you're drawing from a slightly different deck on that second draw. That's why they're dependent. That first draw changed the deck. It changes what you're drawing from. So the odds on that second draw have to be different because the deck's not the same anymore. All right? Okay, so yeah, you see how that one simple thing of replacing the card or not gives us an example of independent versus dependent events. Okay, now to do the calculations, the probability that event A happens, which is you draw any 9, and then on the second draw, you draw any king. Well, according to the multiplication rule, if the events are dependent, is the probability of A happening times the probability of B happening, given that A has already happened. Okay, so the probability of drawing a 9, okay, so there are 4 9s out of 52 cards total. So that's the probability of getting a 9 on that first draw. What about this one? What's the probability of getting any king, given that you drew a 9 on the first draw? Okay, well, this is out of that altered deck. If on the first draw you drew a 9, well, now there's only 51 cards left, okay? But there are 4 kings in that deck of 51 cards. So that's your probability of B, given that A's already happened. The probability of getting a king on a random draw, given that you took out a 9 and didn't replace it, okay? So yeah, that's different up here. Yeah, when you replace the card, it's just like 4 out of 52 odds either way. If you don't replace the card, well, then it's 4 out of 51, okay? All right, so that gives us 16 over 2652, which is still like a little more than 0.5%, about 0.603% chance. All right. A little more likely because, you're trying to get that king out of a slightly smaller deck, but it's not that much different, even though it is a different number. Okay, but I guess like what I really wanted to show you is how to use that multiplication rule, how to think about events occurring in sequence, how to tell the way the math is different if the events are independent or dependent. Okay, now let's do something like I guess with like cards, then I'm calculating the odds based on what I know is in the deck, okay? But we may get like odds given to us from like scientific studies and things like that. So here's an example that I got out of our book, okay? So let's say that there's just some certain medical statistics that go like this. Okay, it happens to be true that 1 woman in 600 has a certain mutated gene. Okay, now in our book there were no more details given about this, probably because the nature of that mutated gene and why it does what it does is complicated and beyond what we would talk about in statistics class. But let's say 1 woman in 600 has a certain kind of mutated gene. Okay, and let's say like generally gene mutations are not a good thing. All right, but anyway, 1 woman in 600 has a certain mutated gene, and then like that's like one fact. Okay. And then, like a completely separate fact is that about 45% of the women with this mutated gene actually go on to develop skin cancer. Okay. All right. So 1 in 600 have this mutated gene, and about 45% of the women with that gene, almost half, develop skin cancer. All right. Sometimes I notice that to help understand the information, these things called Venn diagrams are sometimes given along with the question. So you might see a Venn diagram, and it kind of shows us how that information is related up there. So there's women with the mutated gene, that's what this circle is. And then women who get skin cancer, that's what this circle is. And so it helps you think about it because there's some overlap. Like this part right here, it represents the fact that, well, there are women with the mutated gene that also get skin cancer. That's what this overlap is. But then like this circle right here that's not overlap with that one is just tells us that, well, there are women who get skin cancer for reasons that have nothing to do with the mutated gene. They don't have the mutated gene. So that's what this represents. Okay. So that's true up there. And then there are women with the mutated gene, all right, who don't get skin cancer, right? Now, all that was given up there, right? Because it didn't say 100% of the women with this mutation get skin cancer. It said 45%. So that means that of the women with the mutated gene, some of them are here and get skin cancer, and some of them are here and don't, all right? So this Venn diagram is just meant to show you the overlap of all the information. Okay, some women get skin cancer, don't have the gene mutation. Some women with the mutated gene don't get skin cancer. And then some women with the mutated gene do get skin cancer. All right, it's just another way of presenting the information without the numbers on top of it. Okay, so here are our events this time. Okay, suppose we want to select a woman at random, and that woman happens to have the mutated gene. Okay, so we selected it. There's like all these women. We pick one at random from the sample that happens to have that mutated gene that was mentioned up there. And then event B, which is in sequence with event A, is that this woman selected here in event A actually developed skin cancer. So, what are the odds that, there's the sample space of all women, you pick one and happens to be that she has the mutated gene. There's like a 1 in 600 chance of just that happening. But then, of that woman, she goes on to develop skin cancer. What's the event? Not that this happens or not that this happens, but that they happen in sequence. Okay, now before we go on to the calculations, these are dependent events, right? Because, it did say up there that having the mutation does directly influence the odds of getting skin cancer. That's what this is right here. This right here is what says that the events are dependent, all right? So, okay, if you want to know what are the odds of choosing the woman by random choice that has mutated gene, who then goes on to get skin cancer, according to our multiplication rule, is the probability of selecting a woman at random that has the gene mutation, and that happens to be given, times the odds that that woman with the mutation will go on to get skin cancer. That's the probability of B, given that A already happened. That's also given, okay? Why do I say that? Well, the odds of selecting a woman at random with the mutated gene, well, it says 1 in 600 are like that. So that is 1 in 600. And then suppose we selected a woman at random, that's A, that has the mutated gene. then on top of that, the odds that she goes on to develop skin cancer, well, that's a 45% chance. So that's why this one was also given. So it's 1 over 600 times. It said 45%, but the way we do calculations with percent is to use the decimal form. So that'd be 0.45. All right. Now that works out to be about 0.00075, or you have about a 0.075% chance for those events to happen in sequence. Not very likely at all, I would say. Okay. Now, there were a lot of details in this problem, but I want you to take away this, that you can tell the events as given occurring in sequence are dependent. And that you understand once we write down the multiplication rule for the odds of them happening in sequence, that each probability that we need was given in the initial information. Okay, so let's see maybe one more example. I kind of like one of the ones I mentioned on the first page, because on the first page, I remember that I was trying to get you to think about events occurring in sequence, okay? Right? And get you to think about what it looks like if events occur in sequence, and get you to wonder a little bit about how do you calculate the odds. But I use this coin toss example, all right? So let's say we toss a coin, and say it's a fair coin, meaning that the odds really are 50-50 that you get heads or tails. You got a 1 out of 2 chance of getting heads or tails. So we're going to do this. We're going to toss a fair coin 2 consecutive times. So that's an example of events occurring in sequence. What are the odds of 2 consecutive tails? Okay. All right. So I would frame this situation like this. I would say, well, event A would be like that the first toss is a tails. And event B is that the second toss is also tails. Now, before we go any further, we would need to think about, well, are these events dependent or independent, right? Because the way you do probability calculations on events occurring in sequence depends on if the events are independent or dependent. All right. Well, coin tosses would be independent, right? You know, you toss a coin once, the coin has no way to remember what happened if you pick it up and toss it again. So just think about how could the first toss of a coin have any effect on the second toss of the coin. It would have to be like some really extreme case where you tossed the coin and it hit the ground so hard that it damaged it and then made it more likely to land on tails. But you know, you toss a coin under any other circumstances and then you toss it again, it doesn't remember what happened on the first toss. Nothing about it changes, okay? So coin tosses are independent events. Okay, so the odds that I get 2 consecutive tails would be the probability that the first toss is tails and then the second toss is also tails, okay? Now, since those are independent events, that's the probability of getting tails on the first toss times the probability of getting tails on the second toss, okay? Where that's not a conditional probability. It's just the probability of getting tails at all. So probability of getting tails on the first toss is 1 out of 2. And then because the coin forgets everything and you're starting fresh on that second toss, the probability of getting tails on the second toss is still 1 out of 2. So it's 1 out of 2 or times 1 out of 2, which is 1 out of 4, which works out to be a 25% chance. Okay. So if you tossed a coin 2 consecutive times, about 1 out of 4 of those trials will you actually get 2 consecutive tails. Maybe try it out. Toss a coin twice. See if you get 2 consecutive tails. Toss a coin twice again. See if you get 2 consecutive tails. My prediction is that that'll work out to be about 1 out of 4 times it will happen. Okay? All right. Now, so we got coin tosses. We got drawing cards from a deck of cards. We got all that stuff, right? And then we have survey questions or questions with preformed data. So here, like, we'll need to read this one kind of closely, but I'll summarize it real quick. You know, I wrote this down the way I think I found it on my math lab, and I just wrote it down the way that it was there. But it goes like this. There's a survey of 2,058 adults. And in that survey, we found that 378 of those adults believed that FDR, Franklin Delano Roosevelt, was the best president since World War II. Okay, so that's their opinion, right? 378 out of 2,058 thought he was the best president since World War II. So suppose that you select adults randomly from this group without replacement. So I choose one person, maybe I gather their opinion, and then I take them out of the group, and then I choose another person. Okay, that's what we would mean by without replacement. That first choice is taken out of selection. Now, here are the events that I want to talk about. You choose a person at random from this group, and the first selection believes FDR was not the best president since World War II. And then you take that person out of the group, and then the second person you select also believes that FDR was not the best post-World War II president. Now, once again, we got to think. If I want to know the odds that the first selection doesn't think FDR was the best president, and also the second person doesn't think FDR was the best president, those are dependent, right? Because if I make that first selection and I take them out of the group in consideration of the second selection, then the group I'm picking from on that second selection has one less person. It's different than the group that I made the first selection out of. Okay, so these are dependent. So the odds that the first selection doesn't think FDR is the best, and then the second selection, that person doesn't think FDR was the best either. So this is what I want to calculate the odds of. What are the odds of these two events happening in sequence? Okay, that's what this means. Because these are dependent, is the probability as is that the first person doesn't think FDR was the best president times the odds that the second person doesn't think FDR was the best president, given that the first person didn't either. Okay. Well, all right, let's do this. We need to do some math, like kind of on the side. 378 out of 2058 thought that FDR was the best president since World War II. That means if you take 2058 minus 378, 1680 do not believe FDR was the best president since World War II. And let's say like every one of them, their only options were either he was or he wasn't. Okay. Having no opinion was not an option. So, okay, 1680 out of 2058 do not believe he was the best post-World War II president. So the odds of that first selection, that first person you select not believing FDR was the best is 1680 out of 2058. Okay, then times. What are the odds the second person doesn't think FDR was the best president, given that the first person didn't? Well, if the first person did not believe FDR was the best president since World War II, and if you selected them the first time and then you took them out of the group for the second selection, well, now there's only, 1679 people who don't think FDR was the best president, right? But the group has also gone down by one. It doesn't have 2,058 people anymore. You took that first person out. Now it has 2,057. Okay, there you go. So there are the odds of that first choice, not thinking FDR was the best, times the second choice. Now these numbers are all because of not replacing that first person and choosing from an altered group. Okay. All right. Multiply those together. That we multiply probabilities always when we calculate the odds of events occurring in sequence, and that works out to be about 0.6663 or about a 66.63% chance. Okay. All right. Yeah, that's pretty good odds because most of the people didn't think FDR was the best president. Okay. Now, for my last question, I want to do another variation on this that involves something I brought up in a much earlier video. Okay, so I'm gonna do a variation of this, and I want to do a quick review about something. So, in maybe like 2-3 videos ago, I talked about something called complementary events. Okay, Complementary events are events that together make up all possibilities. Okay? And the probabilities of complementary events add to 1. So complementary events make up all possibilities together between both of them, and their probabilities must add to 1. So here's an example. This is supposed to be an easy example that we can all do the math on pretty easily to show you what I mean. So say we roll a die like this, and it has 1 through 6 on it. Event A is roll a 1. Event B is roll a 2, 3, 4, 5, or 6. Now, isn't it true that between this event and this event, that's all possibilities, right? Complementary events make up all possibilities between the two of them. That's true. Between event A and event B is everything that can happen when you roll a die. Assuming that the die doesn't fall off the table and get lost. Yeah, you roll a die, one of these events has to happen. So between the two of them, that's everything. So they are complementary events. So that's what complementary events are. What about the second claim that the probabilities of complementary events have to add to 1? Let's try that out. So what's the odds of rolling a 1? Well, there's only one 1 on the die, and there's 6 numbers total. You got a 1 out of 6 chance of rolling a 1. What about the odds of rolling a 2, 3, 4, 5, or 6? Well, let's see. Among 2, 3, 4, 5, and 6, that's 5 possibilities out of 6 total possibilities. So the probability of rolling a 2, 3, 4, 5, or 6 is 5 out of 6. Now, my claim is that, okay, this is what complementary events are. Together, they make up all possibilities, and their probabilities have to add to 1. So if I was correct that these are complementary events, and if I did my math right, then the probabilities of these two should add to 1. So let's see, do they? The probability of event A plus the probability of event B would be 1 out of 6 plus 5 out of 6, which is 6 out of 6 and is in fact 1. Okay? So with this example, I wanted to remind you what complementary events are and this fact that their probabilities have to add to 1 always. Okay? All right. Now, I want to do a variation of this previous question I did about the survey of 2,058 adults. 378 believed FDR was the best president. Okay, so we talked about that for a while. But let me summarize it a little bit like this. Okay, just because I want the information to be on this slide. So there were 2,058 people surveyed. 378 believed FDR was the best post-World War II president, and there were 1,680 that did not believe he was the best post-World War II president. 2 people are selected at random without replacement. Okay? Remember? And I want to calculate this. What is the probability that at least one person among the 2 selected without replacement believes that FDR was the best president since World War II? What are the odds that at least one? Well, that does sound different than every other example that I've showed you. But think of this one in terms of complementary events. Okay? What's the complement of this event? Now remember, complementary events together make up all possibilities. So I'm gonna outline these 2 events, and I want you to think, together, do these make up all possibilities? If they do, these are complementary events, okay? So suppose you select 2 people at random, and I'm talking about the event that at least one person believes FDR was best. So here's the way that could work out. First person says yes, second person says no. First person says no, second person says yes. First person says yes, second person says yes. Does that encompass the event that at least one believes FDR is best? Yeah, I mean, all those that's every way it could happen that at least one person believes FDR was the best post-World War II president. Yes. So, but what else would have to be there to make up all possibilities? First person says no, second person says no. So between this and this, you have all possibilities. So the event of neither believing FDR was the best president is the complement of the event that at least one believes FDR was the best president. Because between the two of these is every possible way that asking two people what they think could happen. All right? Now, what did we say? Now, say we can identify that these are in fact complementary events. Okay? How did we say that the math worked out on complementary events? The probability of an event plus the probability of its complement will be 1. So, I think didn't we do this one already? So here's this event we want to calculate the probability of. At least one person believes FDR was the best president. Okay. And then the complement is neither believes FDR was the best president. Yeah, that's the one that we did in the last one, right? That the A and then B, the first selection believes FDR wasn't the best, and then B, the second person, also believes he wasn't the best. Yeah, that's this one. So look, we know this one. So if you did 1 minus this, you would get the one that you're trying to calculate up here. Okay? All right, so the probability that at least one of the two people surveyed thinks FDR was the best post-World War II president is 1 minus the probability that neither believe FDR was the best president since World War II. And we did this in the last example. Okay, so we don't have to do the math again. This was our calculation. This was our result in that last example. If you do 1 minus that number, you'll get this 0.334, which is about a 33.4% chance. Now, I think that's a big problem, because you have to conceive of what this event means. I gave you the hint to think about the complement, but then you got to think what the complement would be. The way you think about the complement is between the event and its complement. They make up all possibilities. Okay, and then once you get that, you have to think of this equation that the odds of an event plus its complement have to add to 1. And then after that, you have to realize, oh, we did the odds of the complement in the last example, so I already did that math there. And then the very last thing is to realize if I take 1 and I subtract that, I'll get this, which is this original probability that I wanted to calculate.